Hi, in this video, we are going to talk about the axioms of quantum mechanics. There are four axioms of quantum mechanics. They were given by in the present form that we are going to talk about by von Neumann in the 1930s or 1940s. Before we get into the axioms, we'll just talk a little bit about the bracket notation. So the main vector space that we will be working with is C2. So vector space that we'll be dealing with in quantum computation is the C2. Vector space is C2. So C2 is just the ordered pair AB, where A belongs to the complex numbers and B belongs to the complex numbers, right? Well, a vector in this vector space, let me denote by psi ket. This notation is called ket, which is just ordered pair AB. So this will be ket psi. Okay, so this will be a vector. Then the dual of this vector, which is denoted by bra psi. So this is bra psi, which will be just a row vector, which will be the conjugate transpose of psi. So it will be A star, B star, where A star means the complex conjugate of A. Okay, so the bracket notation was introduced by Dirac, and it is nice because one can do inner products. For example, if I take the inner, suppose psi is equal to AB, and let's say another vector phi is equal to CD, where A, B, C, D are complex numbers, then the inner product can be between two vectors can be written as psi inner product phi, which is equal to the complex inner product. So this will be the bri of psi, which is A star B star, and multiplied by the ket of phi CD. So this will be equal to A star C plus B star D. So it's easy to work in this inner product notation. So this should be ket psi. And then we also have the, so this is inner product. So this is going to be the inner product of vectors psi and phi. There is also the outer product, which will be written like this. So the outer product of psi with the vector phi is written like this. So this is indeed AB, which is the 2 cross 1 vector, multiplied by the bra of phi, which is C star D star. So this is a 2 cross 1 vector multiplied by a 1 cross 2 vector. So this will give you a matrix. So this is going to be A C star, A D star, B C star, and B D star. So this is a matrix, and therefore it's a linear operator. So this psi phi is a linear operator from C2 to C2. And the way it acts is that psi ket psi bra phi acting on a vector, let's say alpha. So this acting on alpha is equal to So how does this act on this operator act on this vector alpha? This will be just by the usual way, just by the associativity property of the vectors, we get inner product of phi alpha. So this sort of vectors get cojoined and we take the inner product. This is inner product, which is a complex number, which is equal to phi alpha psi. So this is a rank one operator. Yeah, the way it acts is it just psi times some complex number, right? So it's a rank one operator. So with that in mind, let me start with the postulates of quantum mechanics, and I'm going to go very basic in this first uh, part. So let's write down the first postulate. So postulate number one is called the state postulate. Postulate. It's called the state postulate. So the postulate states that the state of a quantum mechanical particle or an attribute of a quantum mechanical particle is just a normalized vector in some Hilbert space. A Hilbert space is a vector space with incorporated with an inner product. For finite dimensional systems, I think that is the correct definition of a Hilbert space. So will be interested in I guess vector spaces which are Cn, which is the complex vector space, n-dimensional complex vector space. Particularly, the state of a qubit will be just some vector in C2. So the postulate number one says the following: the state of a quantum mechanical particle or an attribute of a quantum mechanical particle is a normalized vector in some Hilbert space. Now, depending on which attribute, the vector space may change, but regardless of the vector space, the particle is just a normalized vector. So, for example, the state of a qubit, for example, the state of a qubit so a qubit is just a two-level quantum mechanical system, is a normalized vector in C2. So in Ket notation, the state of a qubit Ket psi will be alpha times this Ket 0 plus beta times Ket 1, where, well, so this is belonging to C2, and where Ket 0 is the basis vector 1, 0, and Ket 1 is the basis vector 0, 1. And alpha and beta are complex numbers, which such that mod alpha square plus mod beta square is equal to 1. So this is the normalization condition. So Ket psi is just alpha beta. So the state of a qubit is a normalized vector in the vector space C2. And this is the way we sort of say that a qubit is in a superposition of the 0 state and the 1 state. So this is a superposition of 0 and this is a superposition state. Okay, so that's the postulate number one. For qubits, we need not say anything more than this. Now, next, we will go at postulate number two. So how do quantum systems evolve? And postulate number 2 says simply that quantum systems evolve in a unitary fashion. So postulate number 2, this will be called the evolution postulate. And it simply states that if I have a state of a quantum mechanical system at, let's say, time 0, then the way it evolves is that the way it evolves is that there exists some unitary operator. So the evolution is governed by some unitary operator ut, where ut is unitary. And unitary means that u dagger u is equal to u uh, dagger is equal to unity. Okay, so the evolution postulate will be related to the quantum gates. So all the quantum gates, whether they are single qubit gates or multi-qubit gates, they will be unitary operators. So these are these are quantum gates, right? So a typical single qubit circuit may look like this. You will start maybe with some initial state ket 0, then you will evolve it using a quantum gate, maybe a unitary operator, and then finally will emerge a state which looks maybe like a superposition state of, right? So this is the evolution postulate. It simply states, so quantum mechanical systems are reversible because unitary operators have an inverse. So one can reverse the circuit by putting a u dagger over here. And say if I start with alpha ket 0 plus beta ket 1, then this will be get back to our initial state. Okay, so of course, we are talking about closed quantum systems, which means that quantum systems that are not um, interfering with, or the environment is not interfering with the main system. Okay, so this is postulate number 2. The third postulate is the measurement postulate. It's a very important postulate. So what happens when you measure the quantum system? Postulate. It's called the measurement postulate. So let's say you have a quantum state psi, which is given by alpha 0 plus beta 1. So when you measure this state, what will happen is that the state sort of collapses. So you will get an answer which is either, so you will get either a 0 or a 1 as an answer. So you will either get 0 or 1 as the outcome of the measurement. In the case of this qubit, and then so this is the first thing that you'll get. The second thing is that you will get probability of getting 0 as outcome is will be mod alpha square. This is if you do the measurement in this measurement is done in 0-1 basis. Okay, so probability of getting 0 as an outcome will be mod 0 square, mod alpha square. Probability of getting 1 as outcome will be equal to mod beta square. And well, the third thing that happens is that the state collapses. So the state collapses, and the state gets, this particular state psi gets projected on either the 0 or the 1 ket 1 vector. So if you obtain 0 as the outcome, the state gets projected onto ket 0. So if 0 outcome is obtained, state psi gets projected onto ket 0. And if so, the final state will be some complex multiple of ket 0. So final state will be e to the I alpha times 0. If a state 1, if an outcome 1 is obtained, then the state gets projected onto ket 1 vector. So it will be some e to the I beta times, I should say over here, not alpha, because we have e to the I phi of alpha, maybe some, and this will be e to the I some phi of beta times 1. Okay, so when you measure a quantum mechanical system, or a qubit in particular, then you will get one of the two outcomes, either 0 or 1. One can label it as 0, 1, 1 minus 1. That doesn't matter. But these outcomes are obtained with certain probabilities. The probabilities in the case of measuring with the basis 0, 1 is mod alpha square if a 0 outcome is obtained, and mod beta square if a 1 outcome is obtained. And finally, the state collapses into one of the possible states depending on the outcome, either gets projected on the ket 0 vector or the ket 1 vector. And so we have just one more postulate remaining, postulate 4. I'll call this as the combined system postulate. So what happens when we have two qubits, or two quantum mechanical particles? So suppose we have subsystem A, which the Hilbert space is given by HA. So, and then the subsystem B, whose Hilbert space is given by HB. Then the combined system of these two particles, the Hilbert space of the combined system, so I'll call it HAB, is equal to HA tensor HB. Okay, where this is the tensor product of the Hilbert spaces HA and HB. So in the case of a qubit, the state of a two qubit system is, so for qubits, the state of a two qubit system is C2 tensor C2. So a tensor product of two vector spaces is another vector space whose dimensions is the product of the dimensions of the individual vector spaces. For example, the dimension of C2 tensor C2 will be equal to 4. It's the product of 2 and 3, and so on. And if let's say I have 0 A comma 0 1 1 A as a basis of HA. So this is the basis of HA, and 0 B comma 1 B as the basis of HB. Then the tensor product system HAB will have the basis 0 A tensor 0 B 0A tensor 1B. So it will be a four-dimensional space with these 1A, sorry, 1A tensor 0B, and finally 1A tensor 1B. So it's a four-dimensional space. And so the most interesting thing happens over here called entanglement. And if you have a tensor product system, we have the so-called entangled state. So for instance, I will have a state which in this state, so we have states in this combined system which look like this. So this is 0A, 0B plus 1A, 1B over square root of so. So these are entangled states. So these are very special states, and people believe that much of the power of quantum computations come from these sort of states. So one is able to produce this sort of states using quantum circuits. And what is so special about that states that so these states are such that one cannot say or one cannot write this kind of states as a simple tensor of states from system A. So this is not cannot be written as a and states from system B. Or one can also say that one cannot say that one cannot refer to one of the systems without referring also to the other system. So one cannot say in this kind of state that the system is in state phi of some subsystem A and state psi of subsystem B. So we'll discuss more about these entangled states and how they can be used to enhance computing. For now, we will stop here. And next time we'll go into more details of the state postulate and later also the quantum gates and so on. Thank you.